Vectors are the foundational data structure in R. We'll see how we can construct them and then use them to construct tibbles, how to do vectorized math and other computations, how to deal with missing values, and how to work with vectors of different data types. So what is a vector? It's a store of an arbitrary number of items of the same type. Here we have two examples. My numbers has 6 numbers, and my characters has 3 characters. Vectors are nearly every object you're going to work with in R. So we see two examples of vectors of length 1. From the user's point of view, they look like they're not vectors. They look like they're a number or a logical. But in the background, they're stored and treated as vectors. The first function you need to know about is the C function, which stands for combine. Here, we combine a vector of length 3 and another vector of length 3 to make the vector of length 6. In this position, we take tis a vector from up here, combine it with 1920, and we get a vector of length 2. C isn't the only way to make a vector, though. There's a lot of nice shortcuts for creating vectors in R. My thinking is if you find yourself doing something tedious, you could probably Google and find a nice shortcut built into R. So here in the first line, I want to create a vector of A 4 times. So that's not too tedious, but imagine it was 250 times. So you could Google how to repeat a character vector several times, and you're going to come up with this function, rep. So rep's the function, and what does it expect? In the first position, it expects a vector. Often that vector is going to be a singleton. So we start with A, for example, and in the second position, by default, you put a number. And that number is going to say how many times to repeat this vector. So I want you to try the following two calls on your own. In the first call, we're going to have the same default action as we have here. So we're going to take the vector A and then 5 and repeat it 10 times. So you're going to get A5, 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 dot, dot, dot. If you want to override the default behavior, there's an input called each. I want you to guess what the outcome is going to be from this code and then try it on your own. R also has a few shortcuts for creating a sequence of numbers. So if we want the number from 1 to 1,000,000, we could put a 1 here, then a colon, then a million. And that will give us a vector with 1,000,000 numbers in it. Sequence has the same functionality as the colon, but it has additional arguments you can use to extend its capabilities. For example, if you want to skip some numbers, you want to count by 2s, sequence can help you with that. In stats class, you're going to do a lot of simulations. In simulations, you want random numbers that follow a distribution. So here I give you two examples. One is using R norm, which is a function that in the first position takes n, which is the number of random draws you want. It has additional arguments that will change the shape of your normal distribution. You can change where it's centered by changing the mean. You could change how wide it is by changing the standard deviation. In the second call, I use RUnif, which takes by default 5 or n draws from the random uniform distribution between 0 and 1. This function, you can change the arguments. If you want random uniform numbers between 0 and 2, for example, you can get that. One thing I did here, which is somewhat useful, is put parentheses around my definition. This is the same as doing an assignment and then typing the name of the object and having it print out into the console. Vectors are the fundamental data structure in R. Lots of operations built into R are meant to work with vectors. We say they're vectorized because they will operate on the vector item by item. So for example, I can say my numbers, which is a vector from 1 to 6, plus my numbers. And R will understand what to do. It's going to say, here's two vectors. I know how to add them together. I'm going to add the first position, and then the second positions, and then the third positions. So 1 plus 1, then 2 plus 2, then 3 plus 3. And if we don't have a typo, oh, I didn't run the code yet, we get the right output. Now, this works for any math. I can take my numbers and I can divide them. I can raise them to the power of my numbers. So here, 1 is raised to the first power, then 2 to the second power, 3 to the third power, and so on. This vectorization is very powerful. In other languages, you'd have to write a lot more code to get this kind of output. We've already seen, when we talked about mutate, a handful of functions that are vectorized and will work directly with vectors such as my numbers. So the square root function knows that when you say square root of vector, you want to take the square root of each item in the vector. Now, one thing that's special about vectorization is that if we give R some code like this, where we say my numbers plus 6, so we're saying take some vector with 6 numbers in it, and then add another number to that vector. But intuitively, we know what we want to have happen. We want 6 to be added to each spot in the vector, and that's what happens. So what's going on? In the background, R is taking this 6 and it's making it into a vector that's the right length. This is called vector recycling. This will only be apparent to you when you do something like this. So here I have the vector, which is my numbers 1 to 6, and I'm adding to it the numbers 1 to 5. 1 to 5 isn't the right length, and I get a warning. So look at the output and see if you understand what happened. What's going on is we take my numbers, or we take 1 to 6, and then we add it to 1 to 5, and then in that last spot, it starts over again. It recycles, and so we get a 1 here. And 6 plus 1 is 7, and that explains this result. So I'm pointing out vector recycling because it's something that you should probably avoid. And sometimes you'll get a warning message like this. Sometimes it might happen without you knowing. For example, if you take two vectors that are actually multiples of each other in terms of length, it'll silently complete the operation. So when you write your code, stick to either adding two vectors that are the same length or adding a singleton. Now, fortunately, when we do this in the context of a tibble, you don't really have the option to get these kind of weird situations. Now, vectorization isn't only for math. We can use vectorization for comparisons. So I can take my numbers and say, which of them are greater than 2? So what's happening here is, again, vector recycling. And it's going to take that 2 and it's going to extend it or coerce it into a vector of length 6 with 2 in each spot. So we can actually get the same functionality using the rep function. And then compare point by point or item by item, position by position, the vectors. It might be clearer if I write out an example in vectors. Okay, so these 3 lines of code are doing the. So in addition to square root, R has a bevy of functions that will operate in a vectorized form. Here are just a few. I suggest you try them out yourself, and you can always use question mark and the function name to get help. We also have a set of functions that will take a vector and will summarize them, which should remind you of what we did when we used summarize. Again, these are just a few of the many functions built into R, and I suggest you play around with them. I'm going to point out paste 0 because this is one of the functions that get used all the time. And what it does is it takes a bunch of strings or characters, it collapses it into a single word or phrase. So if you ran this code, the resulting word would describe you at that moment in time. So a lot of this vector stuff should feel familiar because it's reminiscent of what we did with dplyr verbs. And that's because tibble columns are vectors. This means we can create tibbles manually, which is going to be very useful if you want to test out something. It's always better to test things out on simple, easy to understand data, or if you want to organize your data from a simulation. So here's an example of creating a tibble called care data. I'm assigning it so that I'll save it into memory. I used the function tibble, and what tibble expects is a bunch of named columns. So ID is going to be a column with the numbers 1 to 5 in it. And kids is going to be a column with these numbers and an NA in the data. Random noise is a vector that I use the R norm. I say 5 so that it's the same length as these other vectors. And then I do some extra stuff to make the normal noise a little bit bigger to match the childcare costs. Let's bring this into R. So when I run the code, I see care data show up in my global environment. And I can operate with this just like I did all my other data. So let's just view it. We see we have a tibble with five rows. Yeah, and that's a tibble. So now once we have our data this way, we can do all of the fancy dplyr stuff we talked about in the previous lesson. So you may be wondering, if all the columns in my tibble are vectors, what if I want to get the vector out? And so we have 3 ways to do it shown in this slide. Pull is a tidyverse verb. So it takes data in the first position. In the second position, it takes a column name, and it will pull that out as a vector. Base R has 2 additional ways. One is with a $sign. So if you take your tibble and you put a $sign after it, R is going to say, here are all the column names. So let's put that in. And I've pulled out a vector. That $sign is actually a shortcut for using this double bracket version. So you put the name of the column you want in the double brackets, and it pulls it out as a vector. When we use select, rather than subsetting as a vector, we're subsetting as a tibble. And this is often more useful because if we keep all our data in tibbles, it's pretty tidy. There's a base R way to subset, and that's also using brackets, this time one single bracket. So you might notice that if you compare the base R ways, they're kind of very similar and easy to confuse. So I recommend starting off learning R by focusing on these dplyr verbs because they're a little clearer and easier to remember. When you need to do some more advanced coding, you might go back and study subsetting a little more. So now we're going to talk about data types. And here's the situation. You load some data that you're ready to work with. I made a fake data set for us to work with called care data. And I see that I have kids, number of kids, I have childcare costs, but I really want cost per kid. So to do that, I'll make a new column using mutate. Maybe I'll call it spending per kid. And then, that's an easy division problem. That's childcare costs divided by n kids. All right, so this code is perfect, but we have a problem when I run it. And here we get this error. It says non-numeric argument to binary operator. So in order to understand this error, we need to understand data types. So R has 4 primary data types for atomic vectors, which are the ones you're going to need to know about. These are kind of a technical issue. It's how R stores the data on the computer, but it comes up all the time because you get type errors like we just did. So we need to understand where these are coming from. So if we just focus on these data types, we have logicals, which are true or false, or NA. We'll come back to NA. We have integers, which are like integers in math, 1, 27, negative 527, and doubles, which we can think of as numbers with decimals. So R sometimes will take the number 1 if it doesn't have this L here, and it'll consider it a double. So if you really want to distinguish between integers, you add an L. Finally, we have characters. Characters are things that are put in quotes. Sometimes we call them strings. So what do we do with this information? Let's come back to R. I'm going to make a simpler example. This is a very good coding practice. If you're not sure how something works, make a simple example. So I'm going to make a character, but I'm going to put a number in it. This plus 5 gives us that same error before. Non-numeric argument to binary operator. So by now, hopefully you guess what's going on. A isn't a number in R's world. A is a character. And so it doesn't know how to add characters and numbers, and so it throws an error. So R has helper functions to let us know what type our objects are. So here, if we take A and we say type of A, it'll tell us its character. Sometimes we want to know if A is a specific type, and we can say is that integer A or is that character A and get a true-false response. We can also use type of on a column in our data frame. Here we see that with childcare costs, we have a type double, which is a number which is going to work. But with n kids, we have character, which is not going to work. So we've diagnosed our trouble. So what we can do about it is something called type coercion. I can take A and say as that numeric. What that's going to do is it's going to take the string and turn it into a double, and then it'll add it to 4. And we get 5, as we hope. This is a useful set of tools. We can change the type using as dot, 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 dot. The question I hope you're wondering is, what if we take something that is definitely not a number and we put it through the ringer? In our data, we can see we have a thing called unknown. And what will as that numeric do when we give it something that is not a number? So here is another warning, well actually our first warning, and it says warning message, NAs introduced by coercion. So doing our coercion, which is changing types, R doesn't know what to do. It knows that unknown isn't a number, so it can't just put a number there. We don't want to put 0, for example, because that would not make sense. So instead we have this thing called NA, which is filler. So NA fills in when we don't know what to do with something. One thing you need to know about NAs, though, is that they are contagious. So if I try and add something that I don't know is a number or not to a number, I'm going to get NA. And then when I add NA plus 4, I'm going to get NA. So we'll play around with this in some of our practice, but it's an important thing to be aware of. It's so important that we have our own little function called is.na, which returns true if the thing is NA and false otherwise. All right, so let's take this all back to our data. So the first thing we want to do is we want to take n kids and we want to convert it to numeric. So again, we're using mutate. we're turning n kids from what it is now, which is a character vector, into a numeric vector. If I could be even more explicit, I could say is as integer, because we don't have fractions of children. So now let's think through what's going to happen before we run the code. And again, this is why we like to use a toy example. So these numbers 2, 4, 0, 0 will be coerced into numbers because that's something R understands. But unknown will become NA. And then we're going to divide childcare costs by the number of kids. So we'll have 1,000 divided by 2, which should be 500. 3,000 divided by 4, 750. 0 divided by 0, what does that return? Let's just do a test in the console. Okay, so that gives us NaN, which stands for not a number, which is distinct from NA. And then we're going to have 500 divided by NA. And what we saw above is that NAs are contagious, so we should get NA. So let's run this code. Perfect. Exactly as we suspected. In this column, we see numbers that make sense. We have 0 divided by 0 here, giving us NaNs. And then we have an NA in the final column. Also note that we get this warning message. This is a very common warning message. And now we know where it's coming from. R is trying to change a data type and doesn't know how to do it. And that's all she wrote for vectors and data types.